So now that we have a little bit of a handle on horizontal circular motion, we want to change our attention to vertical circular motion. Now, vertical circular motion is a little bit more challenging. The reason for that is because with horizontal circular motion, what you're going to find for pretty much most cases is that the centripetal force is constant. And part of that has to just, actually, I'm not even going to, no, I won't even bother going into that. I'm not even going to go into that explanation. But pretty much no matter where we've looked on the horizontal circle, that centripetal force has been constant. That made life easy for us. What you're going to find for vertical circular motion, the centripetal force is going to change depending where you are in the circle, and that will have consequences for other forces. For example, if you had a yo-yo on a string and you were rotating it, like here's my yo-yo. So like if I'm at the top of this vertical circle, you're going to find that the tension's not that great there because the yo-yo is going to want to come back down and it's going to kind of create this slack in the string. Whereas at the bottom of that circle, well, the yo-yo is being pulled down because of the force of gravity, and that's going to tug on that string. It's going to pull it nice and taut. So what we're going to find is that the tension at the bottom of the circle is greater than it is at the top. That is a difference in vertical circular motion, or one of them. So we have to account for things like that, which means we also have to deal with the force of gravity a little bit more. We saw it a little bit when we dealt with the horizontal motion problems dealing with like friction and the case of the flying pig. But this time, the force of gravity is going to be significantly more substantial. It's going to play a greater role. With everything, and I can't emphasize this enough, anything with forces, you really have to draw the Freebody diagram. And I will emphasize, for positive convention, we will call towards the center of the circle positive, away from the center of the circle negative. Also with vertical circular motion, there's some special cases. You may have times where it asks you to find this minimum or critical speed of an object at the top of the loop, such that the object gets around and stays in circular motion. Depending on what we have, if we have something like a roller coaster, we're going to set the normal force to be 0. So to find that minimum speed of the roller coaster, we'd say at the very, very, very top, it briefly loses contact with the track. So we'd have that Fn equals 0. Or for example, if you had like a string, something on a string, and you want to see the minimum speed, you'd have to spin it to get it to go in a complete circle. We'd say at the top, the force of tension is equal to 0. So these are special cases. You won't see a lot of these, but they may come up. So let's look at this. So we've got a 4,500 kilogram roller coaster. It's full of people, and it goes around a vertical loop that has a radius of 27.5 meters. So we'd like to determine the minimum speed the roller coaster must have at the top of the vertical loop. Now, the minimum speed is the key here, but let's look at a free body diagram. So here's my center of the circle. Now, not ignoring the minimum speed part for a second, at the top of this, we're certainly going to have a force of gravity. And keep in mind, we're assuming that the entire roller coaster is condensed into a point at the very top. So this has a force of gravity, and the track and the roller coaster, they're in contact, so there is going to be a normal force. The track is going to push against the roller coaster, and it's going to push it this way towards the center of the circle. So we do have an Fn there. But we're looking for minimum speed. So minimum speed, this is going to tell us that Fn equals 0 at the top. So what we're saying in this problem is that for that very brief moment that this roller coaster is at the very top, it's going to just lose contact with the track, and then it's going to successfully make its way around the loop. Now, what that means is on our free body diagram, technically that term is gone. So the only force that we have in the plane of the circle is this force of gravity. So we could say that our centripetal force, it's just equal to Fg. Now we have definitions. We know that Fc is mv squared over r. We know Fg is just mg. So this is going to allow us to cancel out the mass because I have a mass term on both sides. We're going to get v squared over r equals g, or v is equal to the square root of gr. So this is going to give us the minimum speed. So based on what I have, we have this 9.81 meters per second squared. We have this 27.5 meters. We're going to square root all that. And let's see here. Times 27.5. we are going to get about 16.4 meters per second. So this is the minimum speed that the roller coaster has to travel to actually get around that loop. If it travels less than that, it won't be able to get around the loop. If it travels faster than that, it has sufficient speed to get around the loop. So we also want to just look at one other type of problem similar to this, but it's a slightly different question, and there's a little bit of a subtlety to it. So we have a roller coaster. It's in motion at the top of a loop, and this loop has a diameter of 27 meters. Oh, very interesting. So the roller coaster cars, they have a speed of 10.1 meters per second at the top of the loop, and it was found that the combined mass was 5,300 kilograms. So we'd like to determine the magnitude of the force that the track must be designed to withstand at the top of this loop. Right, so once again, we want to draw a free body diagram. So here's the center of my loop, like my loop's kind of coming up and around, so here's my center. So for sure, we're going to have a force of gravity that's going to act down. Now this time we're still going to have a normal force, but notice this time the cars are on top of the loop, so the track is going to push up against, or it's going to push towards these carts, which means that the normal force is actually being directed up in this case. So we have an Fn, but it's actually going up this time. Now, because this object is still traveling in a circular path and the center of the circle is down here, the net force still has to be directed towards this point. So the force of gravity still has to be greater than the normal force, such that we have that curve down here, or the circle center is down here. Because if Fn was greater than Fg, the net force would actually be towards up here, which means our center of the circle would have to be up here. So first of all, that's our free body diagram. Now we're looking for the force that the track has to withstand from the carts. And the normal force tells us the force that the tracks exert on the carts themselves. So if we find that normal force, we're going to find that force that the track exerts on the cars. If we find the normal force, we will find that force that the track has to withstand, because it's a Newton's third law scenario. So Fn is the force of the tracks on the carts. So by Newton's third law, the force of carts on track is the negative of Fn. So if we find that normal force, which is going to be that force that the tracks supply to the carts, well then we know by Newton's third law the force that the carts supply on the track, so that the track has to withstand, is going to be the same magnitude as the normal force, just in opposite direction. So it's going to be directed towards that center of the circle. So with this, we'd like to write out our net force statement. Or in this case, because we're dealing with circular motion, we're going to write the centripetal force. So we're going to have that force of gravity towards the center of the circle plus that normal force. Now again, we want to say towards the center. We're going to call that positive. And we're going to say away from center. That's what we're going to call negative. So this is going to be our sign conventions for this question. So based on what I have, the normal force is going to be this centripetal force minus this force due to gravity. So we have mv squared over r minus mg. So we are provided mv, we know g. R we're going to be a little careful with, because we're told the diameter is 27 meters. What they're really saying to us is that the radius is 13.5 meters, so we got to watch for that. So let's calculate this normal force. So I have 5,300 kilograms. I have this v squared at the top, this 10.1 meters per second squared. We're going to divide that by 13.5 meters. We're going to subtract off the 5,300 kilograms, and because towards the center of the circle is positive and g is pointing towards the center of that circle, we're going to call that positive 9.81. So I have my equation for the normal force. So let's go ahead and calculate that. So there's a lot of terms in here, a lot of places you could make mistakes. Just enter these really, really, really carefully. So what I'm going to get here is I'm going to get about negative 1.19 times 10 to the 4 newtons. Now somebody might see that negative and they might be alarmed. They might be like, oh no, we did something wrong. No, that negative is actually a really good thing. Because keep in mind, if I go back to my diagram, the normal force is pointing away from the center of the circle. It's not pointing towards the center, it's pointing outwards from it. That means by our convention, Fn should be negative. We are getting a negative number. That is good. We're very happy with that. So when we talk about the force that the track has to withstand, we just want the negative of the normal force. So it's going to be this same force in opposite direction. So it'd be the positive of this, which we know is towards the center of the circle. So the force, the magnitude that this track has to withstand, it's going to be that 1.19 times 10 to the 4 newtons, which as we said is opposite direction to Fn. So it's the opposite direction to Fn, but same magnitude. So this is a bit more of a challenging vertical circular motion problem just because we haven't explicitly communicated what we're asking you to find. Like we didn't say find this exact variable. We kind of buried it in the problem. But this is a good question. This really tests, do you understand the positive conventions, the proper free body diagram, and all that lovely stuff we've worked on for the last while in this course.